Let's think back to yesterday. For the benefit of those who weren't there and for the benefit of us who were there and can't remember. Okay? We had a look at a special kind of number. Started with an S. Does anyone remember? Certs. Very good. Thank you. Certs. Okay? Certs are special, and we compared them with two other kinds of numbers. We compared them with numbers like this. Yeah, Ethan?
Is it like elevator music?
Oh yeah, we'll get to. I haven't quite got there yet. So this one before that, this is a terminating decimal. Remember that? Yes, good. So it just stops, terminates. Okay. That's not the only kind of decimal that you were familiar with from last year. We had the elevator music of the decimal world, right? Recurring decimals, very good, right? Which go on and on forever, right? This is 0.33333333. Or sometimes you might have another repeater in there. For instance, one we didn't have a look at was, just as an example, 0.2, I don't know, I'll just pick a random one. If I have two repeated dots, what would that mean? What should that be equal to? Yeah, Adam.
When they repeat the same order?
Yes, that's right. So, can someone tell me what should I actually write? Yes. 27, 27, 27, and or just in case you're curious, that's 27/99. You can verify it with your calculator. Okay. So we looked at terminating decimals. We looked at recurring decimals, and then we said surds. They're weird. They're really, really weird. I think the example we looked at was like the square root of 7. Okay. And it was, it's going to be, now by the way, before you reach for your calculators, do get them out. But before you actually punch it in, I can know right away, even though I don't actually know the exact value. I know that this is going to be somewhere between 2 and 3. Think for a second. How do I know, not just because I'm a maths teacher and I've looked at this number a lot of times, without reaching for a calculator, how do I know it's 2 point something? Let's actually write it down. Let's get the number before we get your answer, Ethan. Get your calculator out now. It's 2 point what? Someone want to read it out for me? Daniel, have you got it there?
Yeah.
Yep, read it out for me.
2.6457513.
I missed the rest. Okay, that's good. Thank you. That's enough. Okay. So, like I said, it's 2 point something. Ethan, did you have a suggestion?
I was just going to say, because like 6, which is 1 less, squared is 2. What? I know. Mind explosion.
Wow, that was so mind blow. I think I'm still recovering. I'm going to go on that idea of comparing with different numbers. Do you want to give us a suggestion?
I tried halving it and then halving again, but that didn't work.
Yeah, that's confusing as well, isn't it? Taking the square root is a bit of a different. Let me show you how I thought it through. Remember this sign here, right? It means square root. Square root for short. Okay? It means think out what is the number that if you squared it, you'd get 7, right? And if you go back and when you've got that in your calculator display, sure enough, if you hit square, it'll give you 7 back. Okay? Now what that means is though, not all square roots, not all of them behave in this weirdo way, right? Some of them are just nice, neat numbers. For instance, you guys know what the square root of 4 is, right? The square root of 4 is the number you square and it'll give you 4. So altogether now, the square root of 4 is 2. Very good. Okay, so that's 2. There are loads more though. Right? So therefore, by the way, the square root of 4 is not a cert because it's a nice, happy, normal number. Okay? Square root of 4 is nice and neat. The square root of 9 is also nice and neat. And it's 3. Right? Now look at this. Look at this. 7 is between 4 and 9. It's between 4 and 9. Okay? So if this gives me 2 and this gives me 3, then I must be somewhere between 2 and 3. You see what I did there? Okay? Let me give you another example and you see if you can work it out with me. Don't shout it out. Just think about it because some of you will get it quicker than others. The square root of 30. Don't shout it out. This is another messy number. It's a surd. It's going to give me some garbage over here. Okay? But if you think about it, you can work out which numbers it's between. Think. Raise your hand if you think you know. You think you know? Yeah? Yeah? Will, what do you reckon?
6 and 5.
6 and 5. Does it check out? How would we know for sure? Okay. 5, right, is the square root of what number? 25, very good. We actually looked at that particular example yesterday. 6 is the square root of what number? 36. Great. And look, 30 is pretty much smack bang in between 25 and 36. So therefore, I'm expecting that it's between these guys. 5 point. Did you work it out?
Yeah. 5.47722557.
Okay, there we go. We get the idea. Thank you. Okay. So you can use this little mental trick, right? Even if you don't know what the exact number is, you know what ballpark it's in, and that's an enormously useful skill as you go forward. Okay. All right. Now that's what we looked at yesterday. But why are we even looking at surds in the first place? You can make a new heading now, which is Pythagoras' theorem, because this is actually the name of the topic. What does, or what do surds have to do with this? Okay. Make that heading. As you're making it, I would like to pose this question to you. Why do we care about surds? Why are surds important? You survived, you guys are what, 12, 13? You survived, 14? You survived, 12 to 13 years of your life without knowing what these things are, and you've just got along fine, right? Not only that, but these are weird numbers. These numbers, they don't seem to occur in nature, do they? These numbers, they're okay, right? It's like, oh yeah, how many houses are there over there? There are 5 houses in a row, okay? How many cars have passed this street? 22 cars, normal numbers. But these numbers are not, right? You never go to Donut King and say, yeah, I'd like root 3 donuts, please, and they're like, yeah, sure, that'll be root $2. Like that, this doesn't happen, okay? These numbers, these surds, they don't come up in nature. Or do they? So, under this heading, let me show you how these emerge. You will need a ruler for this. If you don't have a ruler, I hope you can borrow off the person next to you. Hand up if you do have a ruler. Hands up straight. Hands up straight. Oh, we're pretty good. Okay, hands down. If you don't have a ruler, please go and get one. They're not expensive. I can lend you one, but you really do need one, and it's going to become a bit of a pain for you to constantly borrow. So for now, maybe just use the one next to you. I'd like you to draw some triangles with me. Okay, we're going to draw some right-angled triangles.
I like triangles.
Yeah, great. Okay, so here's the first triangle I'd like you to draw. Okay, I'd like you to draw a right-angled triangle like that. Does anyone remember? Think back to the work you did with angles last year. How do we signify a right angle? What do we put in there? Square. Good. A little square in the corner, like so. So we've got a right angle in there. Okay. Now we're going to draw a variety of triangles today, and we're going to label them and all that kind of thing. Now, it's okay if you've drawn your triangle already, but if you haven't, if you're still going, I'd like this to be a 3 centimeter by 3 centimeter triangle. That's okay if it's not. I just want you to mark it as 3 centimeters by 3. Obviously, mine is not 3 centimeters. I'm just labeling it as such. Okay. Now, 3 centimeters by 3 centimeters. Now, this is a nice normal number to decide you want your side length to be. Okay. If you have made your sides those lengths, okay, and then you get your ruler out again, okay, and you look at what's this third side over here? Now, this third side has an important name. It's the longest side of a right angle triangle. Starts with an H. Yeah, Shane? Hypotenuse. Very good. If you have not heard that word before, do write it down. It's a long one. It's a bit tricky to spell. Hypotenuse. Okay. The hypotenuse of this triangle, when you measure it out, well, you look at yours. Like, how long is it actually in centimeters? Has anyone actually got a 3 by 3 triangle there and can measure the hypotenuse? Morgan? 4.1. It's like 4.1. I'm going to put a question mark there because if you look very closely at your ruler, yeah, you might have said 4.2.
4.2.5.
Question mark. Okay? It's not like right on one of the markers. It's somewhere in between. Mr. Johnson.
Always love Pythagoras theorem.
It's a joy for everyone. We're doing really well.
They're doing really well.
This is a lovely UA class.
Yep. Which group is this?
This is 8M14.
Right.
So we're right down the middle, really.
Fantastic. Well, I'm sure that they look as though they're all engaged. Does everybody understand Pythagoras?
We're just introducing. So we're getting there. We've been looking at these strange numbers and why they're strange. Do you guys remember what's the metaphor we learned yesterday for what surds are? It's we did. Not right. Jazz. Yes, we named surds crazy immortal jazz musicians, and you can hassle one of these lovely children at recess or lunch if you want them to explain that to you.
Yeah, I'm very interested in that.
Great metaphor. So.
That's what Roy Masters used to call the head teacher of mathematics at a school he was working at, Roy the journalist.
Crazy or immortal or a jazz musician? Right, fair enough. Thank you, Mr. Johnson. Okay. Where were we? Alright, now, by the way, does anyone have any other measurements? 4.1, 4.2, do we generally agree? Rachel, do you have a different? 4.3? Okay, it's all still in the same ballpark, yeah? 4.3 is the hipster option. It's like 4.1 and 4.2 are too mainstream for me. Alright, now, there's a problem. What's going on? What's it actually equal to? Okay, now, we'll come to the answer in a second. But my point is, it's a weird number, and we're getting different things for it. Okay? However, not all triangles that are right angled give you these weird numbers. Let's draw another one this time. The dimensions might be familiar to some of you. Instead of 3 by 3, I want to make it 3 by 4. Okay, so 3 centimeters this way. Chuck in your right angle and measure out 4 centimeters. 3, 4, and then you're going to have the hypotenuse over here. Okay, now do try and measure it as carefully as you can. If you've got a grid book, that might help you out, but it's not necessary. The ruler should give you enough accuracy. I want you to start drawing a new triangle. Okay, it's bigger. This time it's going to be 5 and 12. Okay, again, a right angle. Now, as you're drawing that, let's look at this 3, 4 triangle. If this time you measure this hypotenuse over here, with a reasonable degree of certainty, you should be able to find it's bang on 5 centimeters, right? And if it's not, what I would put that down to is just little inaccuracies in your ruler or in the drawing of your line, but essentially you should be on 5, right? You shouldn't be very far away. That's unusual. It's this nice, precise, neat number, right? And if you have a look at 5 centimeters over here and 12 centimeters, again, pull out your ruler. We're starting to get to the limits of most of your workbooks, but 12 centimeters should fit. If you go 5 here and then 12 here, when you measure across, again, you should be very close, bang on, to a nice number, 13 centimeters. Okay. Not only that, but everyone across the room is getting pretty consistent results. Now this is what maths is about, okay? It's not like some people in a room, dark room somewhere decided, nah, let's think of how we can, torment the minds of young children. Let's write textbooks. This is not bad for this book. This is quite a good book. Let's write books and make children study them, which are really, really complicated and random, and make students memorize rules. That's not what it's about. It's about looking at things which occur in, you want to build a building, or you're trying to measure a distance from here to here. Things that happen in real life, and you notice patterns, right? And then we try to understand those. That's what maths is about. So by now, you should have all of these. If you are very adventurous and you have a big enough book, you can draw a third one, which is, I won't draw it to scale, but if you do 8 centimeters along here and 15 centimeters along here, some of you will have a book that's a bit too small for that, and that's okay. But again, you'll find something unusual about the hypotenuse. If you measure it and you measure it accurately, it will bang on a certain length, a whole number. Fantastic. You should find it's bang on 17. Okay? If not, just recheck the way you've constructed it. Okay? So now here's what's going on. You've got these unusual triangles. These aren't the only ones, by the way. There's a whole bunch of other ones. Okay? But these guys are weird. They give you whole numbers here rather than, like most triangles are like this. They give you these weirder numbers, which, as you might be able to tell from what we looked at yesterday, they are surds. And that's why when you measure them, it's like, I don't know, it's kind of from It's some weird number like this. You can't measure that with a ruler. It's not accurate enough. Okay. So the question is, well, what is this actual length equal to? And it was Pythagoras, this ancient Greek guy, who worked out, well, among many other people, who worked out what it was equal to.